In this example of hydrostatic pressure variation in a fluid, we're going to consider what the pressure would be 5 meters below the surface of the water in a swimming pool. So I've drawn that out here where we have a water surface as the blue line. You'll often see in fluid mechanics the upside down triangle with two little lines underneath it signifying the water surface or a free surface. Above that the pressure is atmospheric, so I've labeled that PATM. We've defined our Z coordinate as positive upwards from that surface. And we want to know the pressure 5 meters below the surface at that point P down below. Okay, so from our previous lecture we can write that dP over dZ is equal to negative gamma. And then we're going to integrate that. So we're going to go the integral from negative 5 meters to 0 to the surface of dP over dZ is equal to the integral of negative 5 meters to the surface of negative gamma dZ. Okay, so it's pretty straightforward to integrate. The integral of this left-hand side here, dP dZ is just going to be the integral of dP, evaluated at 5 meters below the surface and at the surface. So that is going to be P at 0 and 4 meters, 5 meters. Right? And then if we integrate the other side, gamma is not a function of Z, it's a constant, so we can pull that out, integrate, and we simply get is equal to negative gamma Z evaluated at 0 and negative 5 meters. Negative 5. Okay, so if we look at working in gauge pressure, then we're going to look at relative to atmospheric. So you have, we can get, say, P at 0 minus P at negative 5 meters is equal to 0 minus parentheses negative gamma times negative 5 meters, right? All right, so we plugged in P at 0, that's PATM. So P atmospheric minus P at negative 5 meters is equal to negative 5 meters times gamma. Okay? We know PATM, the atmospheric pressure, P atmospheric, is equal to 101 kilonewtons per meter squared, so we can plug that in. And we know gamma is equal to 9.789 kilonewtons per meter cubed. We can plug that in. And so we get P at minus 5 meters is equal to 101 kilonewtons per meter squared plus 9.789 kilonewtons per meter cubed times 5 meters. So P at negative 5 meters is going to equal approximately 150 kilonewtons per meter squared, or 50% greater than atmospheric pressure. Okay, so that's a simple example of what the pressure in a fluid looks like. All right, we could do the same thing in English units, but I'm not going to go through that right now. I think you can work that out on your own. But again, the thing to remember is that the pressure in a fluid is determined by the weight of the fluid over that point. Okay. Next, we'll look at a slightly different example.